overall, I'm sure when you logged into Enigma, you probably had to create an account. You probably have an account for your e-commerce platform. You probably have an account for your banking system. So overall, we're trying to tackle with this complexity that of a thing called password. And And guess what? Another set of people really like this complexity, which is the attackers. Attackers know that we as humans are pretty bad with entropy. We are unable to create strong passwords that are unique to us, and as a result, not a single day goes by where we're seeing systems getting breached every single day. These are data breaches of passwords. The most common or the most recent one was just 2 weeks ago, where we see almost 773 million records get compromised, and they were unique password pairs, which is an email address and a password. And it's not just the only one, right? We're seeing these kind of breaches happen all over the place, whether it's from Gmail, whether it's LinkedIn, eBay. Every system is getting compromised, and we're seeing these kind of attacks happen over and over again. And what usually tends to happen in these scenarios is attackers have engaged in a technique called credential stuffing, where they're weaponizing these credentials, whether it's a username and password, and are sending these as targeted attacks to different web properties. So over and over again, just staying underneath the spectrum and just underneath our defensive layers, but just good enough to target our web properties and our web systems. So it's a pretty interesting problem statement. And in fact, the Verizon data breach report last published to say that almost 80% of all data breaches in 2017, and that's over thousands of data breaches that they analyzed, they said were a result of using weak or stolen passwords. So it's a pretty challenging problem statement and something that we wanted to tackle. So as practitioners, right, we all know passwords are terrible. We're saying passwords are terrible. So how do we plan on trying to solve them? They're too complex. They're difficult to type, especially when you think of interface like a mobile device. And I think in general, we seem to agree that they're not so secure. So how are we trying to tackle this? Maybe one aspect of it is, hey, let me add a whole bunch of random characters to passwords. And let me try to make it pretty hard for the attacker. And unfortunately, this actually results back in the original problem statement, which is, as humans, we like patterns. We remember data with patterns. And when we try and create these unique random complexity, we are creating patterns that we cannot remember and retain. So it's just adding to the whole original problem statement. So another thing that is quite common these days is, hey, don't think of a password as a fixed GUID-like construct. Think of it as a long sentence. The interesting thing about this is I am not sure, maybe except conference speakers and actors, I'm not too sure on how sentences roll off their tongue, right? Like, I'm not too sure about sentences, and just scaling it back to the dozens of accounts that you possibly have and every one of those things. Biometrics is something that has recently taken on, mainly due to the emergence of smartphone. I think all of us have experiences with the phones in our pockets, usage of thumbprint, usage of face recognition. It has been pretty fantastic. And the only flip side I can think is maybe from a corporate enterprise standpoint is it typically requires expensive hardware. It typically requires some sort of an upgrade. The other thing that is interesting, which I'll address later in the talk, is it requires an active participation from the user in the sense of, hey, I need to authenticate you, so come in and give me your some sort of a secret that you have or something I am. The other interesting aspect that is pretty dominant and which is quite encouraging is usage of password managers. Now, the flip side, again, is a study from Google back in 2016 showed that less than 12% of all Americans who have a Gmail account were using their password manager. So it's pretty low scale, it's pretty powerful, but we're not seeing as much usage of these techniques. Then, okay, so how about I add more factors? And the factors could be, hey, let me go get a RSA token ID, or let me add some sort of a software-based token generation mechanism. Again, it adds an additional factor, but it's quite easy for someone to say, steal your password, and at the same time steal your smart card, or maybe you want to borrow it to someone for credential reuse and things like that. So it doesn't really solve the problem. And another statistic or a data point from that exact same study from Google is less than 10% of all Gmail users have been enrolled in using two-factor authentication. So a good technique, but not quite as dominant. Again, from the ecosystem space, it just means that the problem statement still exists. Attackers still have a pretty amazing opportunity to go past our defenses. So overall, I think we're trying to tackle this problem by say, hey, let's add more factors. It's something I have. Maybe it's something I know. Or maybe like Thanos would say, it's something I destroy. Or, it's just one of those things, right? Like, hey, what did it cost you to log in? And we're adding all of these layers. Maybe it's something I sacrificed that's a factor for Thanos. I don't know. But it's just an interesting fact. We keep adding complexity to our systems, adding layers. And that in turn, it's a feedback cyclic loop for everything. So in summary, the problem statement that we had and we wanted to tackle at scale is we needed an authentication system that is continuous. Why continuous? Because password, at the end of the day, is a static construct. It is a one-time flow that once you are into a system, you are in unless the system kicks you out. So we needed something that is continuous, that's constantly measuring your risk and your identity, essentially. The other key attribute that we wanted was it has to be adaptive. It cannot be static. It has to adapt over time, over environments, different users. What if someone's sharing? What if someone's using this in a bank account versus maybe seeing pictures of cats? I know. So the notion of risk is pretty important to attestation and a risk of the identity of the user. And lastly, I think as an industry, by adding these layers, we're just we created a pretty complex environment, and we wanted to have an amazing user experience for all of our users. And we want to think hard about those kind of problem statements. So what did we do? So we said, okay, how about we take the notion of behavior modeling of biometric attributes? Now, that's quite a statement, and I want to unpack it a little bit. And what I mean by that is, again, the same notions of using something I am, where it doesn't matter what you type, but how I type. The notions of these have been well known in academia since the 1970s. That technique I just referenced is a technique called Keystroke Dynamics. And there are multiple variations of how I type, how I move my mouse, how I interact with any human interface system on any of our modern applications. There's an aspect of all of those, and we wanted to see, hey, can we use these techniques that help us give us a continuous authentication flow and give us the outcome that we want. So as part of that exercise, this looks almost like one of those Gartner magic quadrants that you might have seen, and my intent wasn't that. And the circles and the bubbles are ad hoc, so don't put any weight into it. But the intent is the X and Y axis are pretty important. And what I mean by that is, so you see the column in the middle, which is biological attributes. And what I mean by that are physical, biological characteristics of the human user. Think your face, your fingerprint, things of that nature. The one to the right of biological attributes is behavioral. So those are the characteristics, again, of something I am that is more continuous, that is dynamic in nature. So we assembled all of these characteristics that could be collected, hopefully without requiring expensive hardware. Again, something that can provide an incredible user experience, and something that can adapt over time versus a static in time, and can be integrated with this overall financial ecosystem that I'm part of. So what we then did was, what I'm showing here are just some of the best performing modules, and I won't spend too much time on it, but I want to highlight some of these key things and why they were super important. Keystroke, something how I type was one of the best behavioral modules that we could come up with, and have metrics and data to showcase its powerful nature. Mouse and touch dynamics is interesting, and we spent a lot of time on it, mainly because most of our modern UI systems are touch. There's probably no notion of a keystroke, say on a mobile device or on a touch device. The keyboard is a touch interface for all intents and purposes. So we had to think pretty hard about the classical workstation-like environment, and also the modern, more mobile touch-like systems. So the mouse and touch dynamics is gives us a pretty good insight when there's no keystroke characteristic. Device is pretty good. I'll spend some time on the next slide. And the rules engine, again, bottom line, unfortunately, when we're dealing with any kind of authentication system is we have to deal with humans and all the support tickets that we might potentially get when integrating this in the future. So what that means is, hey, there's this, I need you to whitelist these kind of things and not train your model so that you don't blacklist or can I wildcard essentially this domain or things like that. So it just allows us to put some rules, and sometimes a rule engine is more powerful than some of the more sophisticated machine learning or deep learning models. So we have that in place. So overall, what did we do? So I'm going to go left, right in our journey here, and layer one is everything that we can collect and measure risk of the device, right? So this is everything called around device analytics. And what I mean by that is any entity that is trying to connect to a property that we need to secure or protect. So let's run a whole bunch of analytics around it. And we can do things like sophisticated device fingerprinting. And you'll be surprised on all the unique characteristics of each device that in turn are able to associate or identify that device itself again, right? And another thing that you can extract if you have partners, maybe your mobile network operator partners, maybe there's a telco or a network provider, there's some interesting metadata that can be combined to that overall device analytics profile. And rules engine, pretty simple and straightforward. What I mean by that is they're bots that are trying to come in. You usually know that, hey, this entity is trying to come in from a known sinkhole, a known phishing domain, things like that, that you can have rules in place to try and identify those characteristics. The next thing, what I have in the middle is layer two. So this is where your actual application or your web interface that you're trying to protect. This is where the entity, the human, either malicious or benign, or a bot that's pretending to be a human is interacting with your system. So you get to collect a ton of metadata around, again, keystroke dynamics, mouse dynamics, any other thing that they are working with from an input standpoint, gesture, pinch, location. So I'm sure as security practitioners, you have a cyber defense or a threat intelligence team that has reams and reams of threat intelligence data. So you want to combine all of those characteristics in here. Even things like, hey, have I been pawned as a password analysis? Now, the important thing keep in mind is you want to do this before the user has pressed that login or sign in button. You have to generate this compute so that you can make a decision on what to do next with that user. And in most cases, what we did, we have observed that something I have provides the most optimal experience for the user of all the factors. And again, these are things that we experienced, the usual TOTP stuff, SMS-based tokens sent to your email address or phone number, things of that nature. Now, in cases, then after the users successfully pass that layer of something I have, you then ship them off to your post, the actual in-app environment. And this has been the best layer so far. And why? Because in this example that I'm showing where we're protecting one of our financial systems is, hey, Ajit all of a sudden is trying to add a new recipient, and he's trying to send the max daily allowed by his bank to a foreign address or a shipping address. Or you know your application quite well. You know which APIs are sensitive. You know which business logic is sensitive. The fact that you can use those characteristics to supplement your overall risk engine is quite fantastic, right? And then you also have a sense of how your user has been interacting with the system over time since they first created the account to how they're interacting with your system today, right now. So you have a pretty nice graph on what they're trying to do with your interacting with your overall application. You can also do other interesting things like peer group analysis. Maybe you have a application that is supposed to interact or only do certain kinds of things, or you have a pretty good understanding that, hey, about 90% of my users, when they come in, they log in, they go generate this report, they open an Excel or a spreadsheet, and they sign out. So for most part, you have a pretty good understanding of what the user is trying to do with your system. And combining all of those attributes to generate your overall risk score, you end up with a pretty sophisticated and a pretty intelligent system. And in case where you determine, your engine determines that something is off, you want to be in a situation where there is a graceful user experience. And for example, maybe you're trying to ask the user that same example where this person is trying to ship off at a recipient and trying to transfer a whole bunch of money to a different account. Maybe you want to ask some knowledge-based input that's an inline flow that's injected to your checkout process. Maybe you ask a secret that hopefully only the user knows, maybe a phone number, maybe some other factor that is pretty graceful, that is within the application without kicking them off and say, hey, I sent you an SMS or something else, go fetch it. It's just a negative experience. So there's knowledge-based input can be added as a field to within your whole in-app experience. So that's what we felt was the overall, had the best experience so far. And you can always punt them back up to an MFA, and it's a cyclic loop. So coming back to how our systems are detecting it, right? This is a pretty nice cluster of the set of all human users, and we have a good cluster that is a bot trying to come into our system, and another set of bots that are trying to simulate and emulate human behavior. And again, the fact that the kind of technology and the horsepower we have today with GPUs, we're able to run the kind of sophisticated models, compute thousands of hyperparameters, go through reams and reams of data, and guess what? As an authentication system, I don't have the luxury of saying, hey, come back in 24 hours and I'll tell you what my score is. This has to be real time. So all of that sophistication, I think we're in a pretty fantastic time where we're able to make all of those decisions in a real-time basis. I want to show a pretty fascinating case study that we found. Again, this was a result of combining models. So going from left to right, these are all the different models that were predicting the outcome. And some of it is, hey, I observed this as normal behavior, I observed this as an anomaly, or I'm predicting this as an anomaly, or I'm predicting this as normal behavior. So there's quite a bit going on. So I'm going to peel the onion a little bit and simplify it. So this is the exact same view from the previous slide, but just more simple on normal behavior and attack traffic. So the one on the extreme left side, all the red dots are attack traffic, and all the green dots are benign normal traffic. The one in the middle, if you observe, it did a good job of identifying that cluster that was attack traffic, but it completely missed that cluster on the left, which, and we have a situation where it's a false positive situation, or a false negative here rather. And then another set of models, again, this is a cluster, a combination of multitude of models, right, on mouse dynamics. The mouse guy did quite well on that extreme left, but it completely missed the one in the middle. So just the fact that we can combine these models, having a sense of our rules engine, our models coming together, knowing their history over time, and doing a peer group or a similarity model gives us a pretty amazing overall trust score, and we're doing quite well on that. And now, finally, some of this work, again, like I said, has been underway since 1970s. Keystroke Dynamics has been around for a while. But if you see, the most published and cited data set or study was done by Carnegie Mellon, and it was a set of about 500 users, and all they were doing, they're collecting this keystroke data for a fixed text of a single password. And there are other studies that have increasing complexity. I think Google, for their ATAP venture, tried to do something pretty interesting. I haven't seen any published metrics on that. So what I want to show is how does it look like when you throw this engine at 1 million users? How does it scale? How does it perform, right? And I have a bunch of false acceptance rate and false reject rate metrics. But the ones, again, like I said, are the best ones were on Keystroke and on our ensemble model, which is combining all of those attributes that I mentioned. And it has a very low false acceptance and a false reject rate. So quite powerful. And again, this is scale at 1 million users. So it works quite well. And one of the things we're trying to do as a team, as a company, is see if we can publish this data and metrics so other folks can investigate, research, and benchmark and baseline as needed. What I want to show very quickly is a live example of this video where one of my engineers, Heng, is typing in my username and password, and it's collecting his overall ensemble score and plotting it out. And at the same time, his location, which is fixed, where everyone's trying to log in on the same machine, is fixed. The device fingerprinting, because everyone's trying to use that exact same machine, is fixed. And those are the two bars that are horizontal, they're flat. But here you see different users coming in and out, and the ensemble model is able to determine that the benign user at the top and how the significant variation is just between a different set of users using that exact same username and exact same password. So again, this thing works and is working at scale for us. So finally, what's next? This is a pretty hard problem statement, and we're trying to deal with things at scale. We're trying to get better at this. The other thing is we're trying to work with the standards bodies, whether it's PCI, with mobile manufacturers, browser manufacturers, standard bodies, and things like that. And lastly, we're trying to see if we can publish this data so that it can be measurable and we can repeat it. So in summary, we have a pretty good situation where using a behavioral biometric technology gave us the tools, the techniques, and a risk engine that is adaptive, it's continuous, and it's giving us pretty good user experience. So with that, thank you, and I'll take questions.